Assalamu alaikum again. Already I've started this chapter as introduction in the previous lecture. I already covered the classifications of relays, okay? And today, inshallah, I will go over advantages, disadvantage of these three relays. So I classified them based on their inputs or their functions, which is we have overcurrent, directional, distance, over or under voltage, differential, reverse power, and under frequency. Already I covered the rule of the relay within a protection system. It could be a protective relay, which its function is to monitor current or voltage, frequency, or a difference in current or impedance based on which you detect the presence of fault or abnormal condition. This is a protective relays. And I also introduce you another types of relays, which is used as auxiliary relays, used for time delay or multiplying the contacts or as a flag. And this is one of I have similar to what I have, which is the similar what I have shown you. This is normally open. This is a normally closed contacts. And we have also other types of relay like reclosing relay, regulating relay that I have already introduced in the previous lecture. Also, I mentioned this, the numerical numbers to identify relays. So for distance relays, for overcurrent relays, each has a standard now. This is a universally number that represent each type of relay. Even the breaker has a number that represents it. Breaker is the 52. Okay. So this also we have. This is the American according to the IEEE standards. But we have also symbols that represent the according to IEC standards. Already classified also the relays based on their technology used. So from electromechanical, this is the first generations of protective relays, to static relays, and nowadays this is the second generation, the third generation now is digital or numerical relays. And also cover this also, where this is still you the history in all electromechanical relays, okay, or they are hardware, okay, and they are based on attractive forces or rotational torques, okay. So it is based on electromagnetic principles. And while in static relays and on a static relay, which is this, or in numerical relays, and static relays also is a hardware. It's built on based on analog electronics or digital electronics. However, after 1980, we have a numerical relays, which is this technology, in which inside here a microprocessor or DSP boards, and now we have which is part of the relay is a hardware like a motherboard in a computer. But also within that relay, we have a software. Okay, so numerical relays, in addition to the hardware, we have also a software that also now I can build the protection functions, the distance relay or the distance overcurrent function using programs, okay, a software. To that software will determine the magnitude of the currents coming from the CT. It determines its phase shift. It can determine the harmonics within that current. I can know, I can compare that current with the settings. I can create a delay. So many things I can do, but all of that is as software. And I already mentioned this on the technology evolutions. Today, I'll try now to introduce the comparison. The comparison, we have, as I mentioned, the oldest relays are the ones that are based on electromagnetic principles. Okay, and that started from 1900 almost. Still, they are existing in the old systems. But the developments, after that, we have another types of relay after 1965, 1970s. So what are the advantages and problems of this? The problem, one of the problem with these electromechanical relays is they are of high burden. Okay, remember from the previous chapter, larger burden can cause also a saturation to a CT, or that will lead to larger class. You know, so there will be a high risk of saturation if you didn't, choose the CT properly. Because it has a moving parts, there's an issues with maintenance. Okay, so it require more regular maintenance. It has inaccurate or a wider insensitive settings. Your settings are limited, as compared to other technology. I'll show you later in comparison. And while because of these disadvantages, the engineers or inventors has thought of using uh, analog electronics and digital electronics to develop new types of relay that has no moving parts. Okay, and that's why we call them static relays. We can call them either static, or you can call them also solid state relays. So these, because they have, let's say, op amps, or they need a DC power supply. Okay, and so they need an auxiliary power supply to function. Relay forms, the advantage of this relay, they form very low burden, okay, as compared to the electromechanical. This is one main advantage. More accurate settings as compared to electromechanical, wider range of settings. You have now a knob, like a potentiometer, where you can change the pickup setting or the time settings of this relay as compared to a discrete values of settings. This is a wider range and a smaller size. The size of this as compared will be smaller, so it will occupy less panel size, okay, or we call it footprint. The space required to install this is much smaller, so it will reduce also cost in general. However, so why the absence of moving bars also the advantage of static relay, absence of moving bars, it will lead to faster operating times. It has also no problems of bouncing of contacts, because we have arcing problem, require less maintenance. However, and also there are compacts, as I say, smaller relay modules and panels. We compare the burden of static relay with electromechanical relay. Like suppose we have an over voltage relay, the burden of over voltage relay is 2 volt ampere, as compared of same type relay. Well, if it is built based on static, it is just 0.2 volt ampere, 1/10, okay, of this. And similarly, if you go to overcurrent relay, this is the range of burden up to 1.3, where here 0.13, also 1/10 of this, okay, and so forth. So static relay has a lower burden as compared to electromechanical relays. However, with this type of technology, it's ended. It's not almost dead now. It's up to 1980. Most of the current developed, what's the issue with this is that it is still not flexible, okay? It's still limited, okay? You cannot build, once it's built, you cannot add or, modify things, okay? Because once you solder op-amps or diodes or whatever, or transistors, you cannot change the circuit anymore, okay? You cannot upgrade it, okay? So that's why we have, in 1980s and after, they developed the numerical relays, okay? The microprocessor-based relays. So these are based on microprocessor and DSP technology. Is provide additional features as compared to the static. Not just is very small, okay, smaller, okay, or occupies and compact, but has also you can add many protection function within the same relay, okay? And because these functions like a library, okay, you can add protection functions you select from library which one you want to activate. It requires smaller panel size. It has this feature, self supervision of hardware and software. This relay knows if something wrong within it. Okay, while in the previous technology, you don't know if this would work correctly or not, or something wrong, unless you do a regular maintenance and check it during shutdown of systems or during maintenance period, preventive maintenance period. While this one, it can check it's within, if something wrong with the memory, it will give you a warning that you come and check me, or okay. So it has self-supervision features, so that will improve its reliability, okay. To integrate protection with measurements and controls, not just, it can measure, it can detect faults, but also it can show you the power flow, the current, the voltages, the power factor, it can do measurements also. It has also control actions. It also has a communication module within it, okay? While this is not applicable to the previous technology. Faster testing and commissioning with this, okay? And this is, before you operate a new system, you need to try to test if it would work correctly or not. So commissioning time, testing time takes a lot of time, before you put the new system into service. Now, with these types of relays, you can test them quicker so that you can put the systems in service quickly. Like this is what I like about this. It's like this is the flexibility within, numerical relays. These represent the library of the protection function. We have an overcurrent relay. This is the symbols for IEC, and this is the numerical number that represent time over current relays for according to IEEE. This is the instantaneous over current relay. Anyhow, so we have a library of protection functions, and you can choose which one we want to activate them within inside this relay. And it's just a matter of how much you can add. It depends on only your limitation is the memory, which is within the relay, okay? While, in electromechanical relay, the 51 relay, you have one relay dedicated for each phase. So in the previous chapter, when I discussed CT class selection, and one of the examples I showed you, I have for just 3 phases, I'll have one CT here, one CT here, and one CT here, and this will go to one relay. This one relay, and this is another relay. So these are the phase relay. So 1, 2, 3 now they represent these ones, okay? And then I'll have another ground relay. This is electromechanical principle, and these are star point. So how many relays I have used? 4, okay, just as an overcurrent relay. So that if we have a panel, this will occupy more space. While now I have just this is as a software, it's not as a hardware. Okay. So these functions are as a software. This is an example of a numerical relay from Speicher Engineering Laboratory. It's a relay manufacturing company. So now I have a display. I can change. I go through the settings. No. So how many functions inside here? You have, this relay for transformer protection. Okay. Now this transformer, I have CT at the high voltage side, CT at the low voltage side. This is the circuit breaker, and the grounded. This is maybe this is star probably side. With the star point is grounded. This is the ground side, and the ground, say I have a CT here, which is this one. And so that from this I can detect if there is a ground fault or not. Okay, and I have here, I can measure the temperature of the winding, of the transformer winding, and here it is the VT. And this is CT1 at the, and this is also a CT1. This is also a CT.
Victor?
Yes. Yes.
Always.
تفضل.
دكتور، هي بس كونكشن واحدة للسيتي بروتكشن، يعني الترانسفورمر بروتكشن ريلي، هي توصيلة بس واحدة ما تتغير؟
No, it depends on, it depends on how many functions you want to implement. Now, in this case, you don't have some transformer. So smaller size transformer, I might have, I don't want to save this, okay, CT, okay. I don't want to have a VT. Okay? I want to just have two currents. I want to implement just differential, okay. Or I might have only one here, one CT here. So it depends on the capacity or the size of the transformer, okay. The protection functions you want to implement, okay, varies, okay. The more protection function you add, that makes this is, you need more CTs and VTs installed. That make the cost is higher. So you want, but the cost is justified for very expensive transformer, for large transformers, okay. And so I would say no, it depends. I might not use this, okay, as input. But however, this relay can be built to have all of these functions, but you can activate, if you don't have VT as input, you disable all these functions that require a voltage as input, okay. However, I can still activate the differential, the overcurrent, this. If I don't have this CT, I will disable these functions, okay. If I have no temperature measurement of the winding, I will disable this function. So as you can see, all these functions are available in the relay, but you can activate them if you have the proper inputs, okay. So they are built to accept so many functions within for transformer protection. So this is
constant connection.
نعم.
More constant connection.
No, it's not a connections, but the relay manufacturer will build it in such a way it can accept a voltage as input, current as inputs, maybe several here. This is not just one wire. This is 3 wires, one for each. There is 3 CTs here, one for each phase. While this is only one ground wire, so we have only one CT here. So this is one, one wire. It's like one pair of wire. Okay. So this is like these two goes to this input. While this is also 3 wires here. This is VT, 3 wires. Okay. So this is 3 phase, maybe a star, YY connected VT. So we have 3 out. So some functions like an over voltage, if I want to know the voltage here, high voltage or not, this is an element that detects that this voltage is high or normal, okay? If it is under voltage 27, so it requires voltage as input. The power, I need a voltage and also I need a current. So the current comes from the CT and a voltage input comes from the VT. So that will measure the power. Is the power flow in this direction or in this direction? Okay. And V over voltage over Hertz, V over F. This is another type for overfluxing protection. So it needs a voltage as input, and I need also to measure frequency from that voltage. So these so many functions are built. So the idea of presenting this is that these types of relay have the facility or the feature that they can build so many functions within them as a software. Okay. And it's just a matter of connecting the inputs required to implement these functions. So you can enable or disable depending on do you have the inputs required for those functions or not. Okay.
Okay.
And this is the input where I can connect a laptop, my laptop, to test this one, or to access to the memory, to access to settings, to access readings. I can, okay. So these types of relays can be used now. The old relays only as a protective relays. Now these relays also can have a monitoring, measurements, control. It has also a communication module. Okay.
دكتور
Like this types of relay. This is from Siemens. Siemens. It has 64 protection functions are there. So these are the yellow ones. This is overcurrent, instantaneous. It has negative sequence overcurrents, has a differential, okay, and it has like communication module. I can connect it through RS-232 or 485. It has this measurement module, okay, to measure the voltage, current, power, VARs, power factor. It has synchronization functions. It has also a logic where I can add if this current is high and the breaker is open, and that you can build logics. It can record the fault waveform before fault occurs and during faults. Okay, and you can look at it after all. This is not possible in the previous technology. Okay. Somebody want to ask something before? في أحد كان عنده سؤال؟
Yes, دكتور.
Yes, go ahead.
The previous relay دكتور.
Yes.
يعني هم بيستخدموه هاي الأيام الحالية هذه وهذا الريلي ولا في أشياء ثانية؟
أيوة الليتست هو الحين هو numerical relays. Okay.
Okay.
And now they call them IEDs بدل مو numerical relays. And I means intelligent, E electronic, and D represent device, intelligent electronic device. And this is the name. Now, instead of calling it a numerical protective relay, is IED. Because it is very smart now. It can do protection, measurements, communication, so all integrated in one design. That's why the terminology used nowadays is IEDs. Okay. This is how we carry the testing. You don't need just a laptop, okay, which you have presets of programmed set of testing scenarios that you want to check, and you just connect it to a relay panel. This is the numerical relay on the panel. So many functions are there, okay, you want to test. So with that one, it's automatic. It carries the test one after another and to give you a report and the readings. You know, with the older technology in electromechanical and static, it takes a very long time to test those types of relays. This is the a comparison also in terms of the for electromechanical relays. We have a characteristic, which is operating characteristic, the relation between operating time versus the volt current, or so normally it's inverse characteristics like this. We have different types of characteristic. We have extremely inverse, very inverse, okay? And these characteristics, okay, will be implemented in electromechanical by one type of relay. So each of these can be implemented by different relays, okay? While in numerical relay, this is as a mathematical equation, which is just, you know, built in as a software, okay? Similarly, the settings in numerical relays over current settings, we have here a plug settings. We have just limited 7 steps, 7 values to choose. At 50% of 50% of 5 ampere, which is 2.5 ampere, I can choose 5 ampere. Okay, then 7.5 and up to 7 steps, up to 200%, which is last tab is 10 ampere. So you cannot have, you want to choose a settings, let's say 2.7, you cannot choose it. You have limited type of pickup settings. The pickup setting is the setting at which relay declares there is a fault, okay? While in static relay or numerical relay can have a step of 0.01, okay? So it's very fine, a wider, we call it wider range. I spoke about the burden. I'll go over now the types on each technology. So I will go over the electromechanical type today, and if I have time, I'll also cover the static types. So we'll go over the principle of operations, how these electromechanical relay operates, what are their types, okay? So the electromechanical relays are classified into 3 types: attracted armature type, balance beam type, and induction type. Induction type also can be classified into 2 types, okay? Induction disk type, and induction cup type. Inshallah, in the induction disk type and induction cup type. Attracted armature also can be classified into 2 types, okay? Hinge type, okay, which is this one, the hinge type, and plunger type, the 2 types. And plunger. Okay. So for the attracted armature type, which is either hinge type or plunger type, this is the one I started with today's lecture. Okay, before I start recording it, I showed you the attracted armature type, where this is a pivot point. This is a coil wound on a core, and you have a pivot. This piece of the relay moves. Okay, moves towards this direction if you pass a current here, right? So if the current pass here, if this is energized, if the current pass here, it will generate a magnetic field, and that magnetic field will attract this arm towards the coil, towards the core. So once it moves, these two contacts will close. Okay. Now they are open, these two will get closed by this part. And now of the current list, now this current that generates this magnetic field will try to make a force, attraction force toward this direction. This is the operating force. And try, if the operating force is larger than the spring force, and this spring force is, we call it the restraining force. Now this spring is fixed somewhere in the casing of the body, so it is fixed. So during normal operating condition, now there should be a current that will make this force. Now this force is proportional to the current, this current. Okay, so this to the square of this current. Okay, if this current is if this force larger than spring force, this contact will be closed. So we are here comparing forces. Okay, this types of operating force versus. So relay operates if relay operates if not, operating force greater than restraining force, greater or equal. They are equal. Just equal means the tendency, it won't move, but it has the tendency to move. But short will operate once it's greater. Now we'll choose the number of turns. So this force depends on the number of turns, the current that will pass. Okay, that will generate a magnetic field strength strong enough to pull this arm, okay, towards the closing these contacts. And this normally is DC DC supply, but we can also AC supply. So we can use these for different applications. Okay, we can use them for as an instantaneous relays. Now, if the current's higher than a certain value, this magnetic field is larger than the spring force, this will close immediately. Okay. We can use them for under voltage, over voltage relays, auxiliary relays. This is the second type, which is the plunger type. Plunger type is the core. The core is moving here. This is the core. Like this is a cylinder on which the coil is wound. Okay, which is this coil. Now inside here is an opening through which they have the plunger is the core. Okay. Now, if we have this plunger, the plunger or the solenoid is also fixed by a spring. Now, once you energize this current flows here, it will generate a magnetic field that will create a force attracting the plunger inside the core, and that will make this contact and this contact to close. Okay. So these types of relays works based on electromagnetic force comparison. Okay, forces of this force. This is the operating force now, and that's the spring force is restraining force. Okay, so the working principle that the net force is the force difference between the operating force minus the spring force. If the net force is positive, means relay will operate. Okay. If the net force is negative, means the operating force less than the restraint force, the spring force, this relay will not operate, right? This will stay as it is. Now, to know what is the This force, the operating force, is proportional to the flux square, and the flux is proportional to the current. So the flux is proportional to the current, okay, and so we have the force, operating force, depends as a function of the square of the currents, and from that I can say the operating force is equal to a constant times a square current. This constant depends on the core size, depends on the number of turns of the coil, depends on so other factors. Okay, so these equations will be Ki square minus Fr. Now, what will be the current required for the relay to operate? Now, the current can be obtained by setting this equal to if Ki square equal to Fr or greater, the relay operates. So what is the current at which the relay on the verge of operation, just about to operate, when these are equal? Okay. When Fa equal to 0, so Fo equal to Fr, so this is the constant K times, so this is K times IB squared. The IB here, the value of current I at which the operating force equal to the restraining force, equal to Fr, from which I can find the current, okay, at which the relay operates. This is the second technology, is the second types of electromechanical is called balance beam. Now here I'm using a spring force, okay, and the operating force are generated from the current that will flow on this coil. While in this, I can use two coils, and each coil, you know, have introduce a force. So this coil, it has this force F1, and this coil produce a magnetic force in this direction. Okay. Now I have like a piece of beam and pivoted here, so it's like نفس المرجحانة. Okay, it's like a balance beam. If this force one, let's say we call this, if this force larger than this, so the beam will be like this, right? And this will become like this, right? And these two contacts are not, will stay open. But so if this force, so we can call this as a restraining force, a force that will tends to, it will prevent relay from operation. While this, if this force is larger than this, it will make the beam, okay, this direction. So this will move in this direction. So this will become closed. So this is, we can say this is an operating force. Okay. So, and we can call this operating coil, and we can call this restraining coil. So instead of using a spring principle, I use another signal here instead of the spring, okay? So with this signal, we can call this signal restraining quantity. I can use here a voltage or a current as a restraining quantity, and here we can call this also as an operating quantity. So now we can compare still. So really operates if not greater than Fr, okay, or if this signal is larger than this signal. The third types of electromechanical relay is the induction type. Okay, induction types like induction motor. Okay, so basically it is like a split type induction motors, and now as I mentioned, induction type, it has two types. We have a disk type and a cup type. this is because an induction motor, no, based on induction principle, it won't work with the DC inputs. Okay, it's only operate when you have an AC. Most widely used among electromechanical relays, this types of relays. Rotor is either a disc or a cub, as I mentioned. The rotor of this relay is either that's why we call it induction disc type or induction cub type. I'll show you later. And the rotor, which is the disc or cub, are made of non-magnetic material like aluminum. Okay. The working principle. This is the one I want to show you. This is the electromechanical relay, which is induction type, induction disc type. Okay, this is the disc, which it moves freely. Okay, around this axis. And once it moves this part or the moving contacts towards a fixed contact, which is this. So if these touch this, the relay operates. Now, as a construction, I'll come to this later, okay? So the disk moves within iron, the core. This is the core, right? As you can see, it is two types. This is the core. Now I have a flux here, and this is a small piece here. Okay, I'll show you why do you have this. Okay, so we have a flux coming here and a flux coming here that penetrates the disk. And these fluxes, I'll call this phi 1 and phi 2. Okay. Now, what's the working principle? What's happening? I will show you now how torque is developed on the disk that will drive it to move based on phi 1 and phi 2. And phi 1 and phi 2 are generated by a coil here. So it's in principle, this is like okay, something like this is the core. This is the cross-sectional area. And here is the coil. This is the iron core, which is this part. And we have a coil here. And the coil from the CTs. So we have a CT here. It's connected to this. Okay. So, and the disk is somewhere here. And pivoted somewhere. And now I can, this two fluxes pass here. Two fluxes, one pass this side and one pass in this side. So I want to phi 1, phi 2 now. We'll see. I will just show you how this disk moves. Okay, what are the forces generated on the disk that cause a movement, a torque? So the basic principle of this induction disk type, that if we have two fluxes, phi 1 and phi 2, that penetrates this disk, okay, and this phi 1, we'll assume in general phi 1 is phi 1 as a sinusoidal. It's like phi 1 maximum, phi 1 peak sine omega t, phi 2 peak sine omega t plus theta. So I'm assuming phi 1 and phi 2 are not in phase. So they are displaced in space and displaced in time. Displaced in time, there is a phase shift between these two fluxes, and displaced in space means they are not at the same physical position. They are physically at different, right? Physically, this flux penetrates a disk at different position than the other flux. Okay. Now, if the flux pass through a disk or like induction, like the rotor of induction motor made of squirrel cage, now we have just a disk which represents the rotor now. If the flux phi 1 penetrates this, and it will induce an EMF, okay, because of that flux and pass it through a conductor, an induced EMF is generated in that, and that induced EMF will produce also a current, eddy current flows within that disk. And this current produced by the induced EMF will try to produce a flux that opposes to the one that has generated, right? This is based on Lenz's law, okay? And this is just a machine's machine principles from machine's course. So now phi1, once it's generated based on now motor principle, which is the left-hand side rule, I have a flux, okay, a current. The flux is in this direction. Now, for a current to produce a flux that opposes this, it has to work on the other directions. So this is the flux, the current that's generated due to this flux from the induced EMF, okay. And similarly, phi2 is in this direction, and once it penetrates, will induce EMF in the core that produce also phi, a current, induce EMF that will produce also a current in this direction. This is I phi2, not phi1. And now this current will try to produce flux that opposes the one that has generated it. And now the interaction between the flux 1 with the current produced by the other flux will produce a force. So force 1 is the flux 1 times the current of produced by flux 2, and similarly for force 2. Okay. And now the net force between these two, the net force will be proportional now into phi1 minus phi2, okay. And now phi1 is phi1 flux 1 times I phi2, and similarly for this is for force 2. Now, if we assume that the flux is sinusoidal and are phase shifted with theta, then when I take, I know that the current is proportional because the induced EMF is equal to nd phi by dt, right? So the induced EMF is proportional to d phi by dt, and because of this, the induced EMF will produce a current also proportional to this induced EMF, okay? So the induced current is proportional to that voltage induced, the circulated current. So the current circulated is proportional to the induced voltage, which is proportional to d phi by dt. If you take the derivative of this, I'll get phi maximum cosine omega t times omega, right? Times also omega. But I didn't put it, just proportional to phi maximum.
دكتور
Yes.
هاي الألفا proportional يعني؟
Alpha is a proportional, yeah. This is means proportional.
Okay.
And similarly for the current I2 produced by phi2 is proportional to d phi2 by dt. And when you take the derivative of this, it will be proportional to phi2 maximum cosine omega t plus theta times also omega, okay. Now, if we substitute this here in these two, I phi1 and I phi2 in these two equations, and simplify, we'll get this, that the force, net force, will be proportional to phi1 maximum, phi2 maximum, peak, sine theta, and theta is the angle between the two fluxes. As you can see, now this net force is proportional now, the developed torque proportional to this force, the net force. And the net force also can be, the phi1 is proportional to I1, phi2 to I2. This also can be written in the same way. And from this equation, as you can see, this equation, which is net force or net torque, if the angle between the two fluxes is 0, the torque developed or force developed, net force is 0. So there will be no movement of the disk if you keep these two fluxes in phase. Now, how do we split these two to be out of phase? Okay, by adding this shaded ring. Okay, it's like a coil, a ring. Once a current passes through that ring, it will induce also EMF in that ring, and that, because it is a closed ring, it will induce a current in it. A current passing try to produce a flux opposing to phi1 that will delay it, okay, as compared to this one. So the function of this shaded ring is to delay phi2 or phi1 as compared to phi1. And as a result, I will have, a rotating torque, okay, due to, splitting, due to the phase difference between these two. And I'll have maximum torque when this phase displacement is designed at 90 degree. Okay. Now we can make this now. These two different types of induction disk. This is the cross-sectional. This is the core, and this is the winding. Okay, and this is the disk. Okay, and this is now, once if you pass a current here from CT, okay, it will generate flux in the core, phi. But this flux will split into two. One is here and one through the shaded ring. So this is phi1, let's say, and this is phi2. Now phi1 is not in phase with phi2, okay, and that will cause a torque, okay, a movement in this induction disk. Similarly, we have, this is called shaded pole type. We have also another type, wattmetric type, where we have two coils. In instead of shaded ring, we use two coils. One coil is connected to a voltage from a VT, for example, and this is from a CT, okay, a coil. Now this coil, the current here will produce a flux phi1, for example, and the voltage applied from VT will produce, okay, also flux phi2. Okay. So we have two fluxes that are not in phase. No, the flux from the voltage coil is different than the flux from the current coil, and you have two fluxes that are out of phase, and that will create a torque. And similarly, we have, now suppose we don't have a coil, a voltage, we have just a current. So suppose I have a CT here, and this CT will be connected to here. So in this case, I have now a current pass here will generate a flux, okay? A flux in this core. And also, so these are the fluxes from, this is phi1. And similarly, I have another coil wound here on the same core of the this coil. So this flux will induce EMF across this, and that's induced EMF. These two coils are connected in series. Okay, so this induced EMF will produce a current because this coil is closed, the second coil is closed, and this current will produce another flux, phi2, and you have phi1 and phi2, okay? Phi1 due to this current, phi2 due to the induced EMF, okay? and they have two fluxes out of phase, and that will produce also a torque. This is the principle. This is the how we implement it here. Okay. No, this is the shaded ring, which is this type. Okay. Shaded ball type. So in this construction-wise, I have a relay, induction disk relay, and this is for overcurrent relay. Okay. On the top, so this is the disk. Let's move on this axis, around this axis. And this is on top. I have, I can move this, this is for control timing. We call it time multiplier. Okay, there are time settings. I can make this closer. This is a moving contact. I can make it closer here or farther away. If you keep this one farther away from it, takes longer time to travel to reach the fixed contacts. So I can increase the operating time. Okay, while this here, I have one plug. A plug is just a piece of bar. If you insert it inside here, it will you will change the turns, the number of turns, effective turns of this. So it's like this winding. You have several tabs. So you have one tab here, one tab here, one tab here, and the plug. So all of these are connected together and goes to the CT. So if you put the plug here, so you connected the full winding. If you connect the plug here, remove it from here and put it here, you connect the fewer number of turns. So you control the number of turns to control the MMF. Okay. MMF, وبالتالي I will which is MMF is NI, no? So controlling this, I control MMF, بالتالي I can control the flux in the core. So that's why I can change the current pickup setting. At higher number of turns, I need less current to produce same MMF. Okay. We have also here, so this is control the currents, right? I can choose the pickup setting, current setting by changing the number of turns. The initial position of the moving contact, okay, with respect to a fixed contact, is control the timing, and this is just this damping magnet is used for calibration. Suppose this relay at this as 10 amperes should take, let's say, 10 seconds, and if it works more than 10 seconds, you need to slow it down by adjusting this magnet. This is for calibration purposes. So this is the relay. This part, this is another relay, okay? Different than the one I have explained now. This relay just used for indication. If this relay trips, okay, if this contact is closed, it will energize the coil. This is attracted armature tab, okay? This is like a hinge type. This is the hinge that moves, okay? Once this is attracted, so this flag will go down and indicate this is a red sign that this relay has tripped. And these are the contacts. Some of them normally open, some of them sometimes normally closed. Okay, so you can have multiple also contacts output from this relay. And this is the induction disk as in symbols only. This is wattmetric type, where I have a coil connected to a current for a CT, another coil to a VT. This is induction cup type. Here this is the iron core, and this is one coil in series with the other coil. This is another coil. So we have 4 balls, and the rotor here, rotor is like a cup. Okay, it's made of aluminum. It's like a glass, but it's made of aluminum. Okay, it's a cup. and this is your rotor. Now, this types of relays is very sensitive, okay? So we use it for compare two quantities, I1 with I2, use it for directional comparison, okay? But its work is the same. The torque develops proportional to current I1 in coil 1 and current I2 magnitude times the sine angle between the two currents, phase angle between this current and that current. And this is the restraining torque, which is a spring force. Even this electromechanical relays, we have a spring. This is a spring is somewhere here. That if you de-energize this moving contacts will go to its original position, because once it is energized, it will move. If de-energized, it will go back to its original. Which moves it back to its original is this spring, okay? Which is this spring, for example, to return its back. This also has a spring by which it will return back to its original position. And these are general equations that represent the torque for different types of relays. Okay, and this is the characteristics of the relay, operating characteristics, the operating time versus the current, okay, or multiple of pickup currents. The multiple pickup current means what multiple pickup currents? The input current over I pickup. I pickup is the current at which we set the relay. You know, this plug setting, we put maybe this plug will give you, let's say, 2.5 ampere operating time. This plug here give you 5 ampere. Up to here, maybe here at 10 ampere. Okay, that's why we have limited, you know, number of selected pickup values in electromechanical relays as compared to numerical relays, because we have limited number of taps. Okay. Now, now this is the pickup setting that we choose. Now the current input is greater than this, relay will tend to operate. So where is the pickup setting? Is pickup setting somewhere here? This is I pickup. Okay, so any current higher than I pickup, any current lower than pickup, relay will take infinity time to operate. So it means it won't operate. Any value higher than the pickup, let's say if this is set at 10 ampere, we choose the 10 ampere and I apply 20 ampere twice the pickup setting, then it will take, let's say, this operating time. Now if I take 3 times the current, it will lower operating time. So the characteristic is inversely proportional. The larger the current as compared to the pickup settings, the smaller is the operating time. And so this types of relay, we call it IDMT characteristics. Inverse definite minimum time. Inverse because inversely the operating time is inversely proportional to the input current. And definite minimum time because even at extremely large currents, the operating time will not be lower than a specific value. This is the minimum operating time for this types of relay, even if you inject extremely large currents. And I can change this curve to the other curve by choosing, by moving this knob, by moving it this further. By moving this further from the moving contact, moving further from the fixed contacts, I'll be able to make the operating time longer. Even if you inject this current at that setting will be this. Now, if I move this further with this knob, if I move this farther away, it will take longer time. It will take this time at the same current. Okay. So this is moving this curve, moving the time dial. We call it time dial or time dial setting or time multiplier setting, TMS or time dial. This is the time dial. The time dial. All right, so we have, just I will close with this. We have different standard characteristics. IEEE has defined operating characteristics, standard operating characteristics, the operating time versus the multiples of the tab setting or pickup setting. When I say here, like instead of putting 10 ampere, 20 ampere, 30, we can, instead of this, we can put when the current, we can put the ratio of the current with respect to the pickup setting. So instead of IB, I can put this is 1. 1 means the current is, so this is I now, axis, while here I have the plug setting multiplier, we call it. Multiple of, which is plug setting multiplier, which is IB, the current divided by IB. Now, if this is equal to this, means 1, right? So means 1 means the pickup setting. If this is 2 times IB, if I inject a current 2 times IB, okay, if I divide this by IB, this is 2 now. This is now 3 IB. This is 3. And up to, let's say, 10. 10 means 10 times the pickup settings. So the higher the current as compared to the pickup setting, the lower the operating time. And now we have IEEE defined different standard curves. We have extremely inverse, very inverse, inverse, okay, characteristics. Each of them with different slope. The extremely inverse has sharper slope, okay. The inverse has flatter slope, okay. And each of these relay characteristic has an equation in this. I will stop today at this slide, okay, and inshallah next class I will cover the static relays. Okay. Let's stop recording.